update on a set of projects that we have all relating to the integration of rangeland monitoring data sets and models to support development of new models and new indicators to evaluate rangeland health, to deliver indicators and models to our stakeholders, and to apply the models and tools and indicators to understand more about ecosystem changes, what the drivers of ecosystem change are, and how effective different conservation practices might be across grazing land ecosystems largely. And the projects I'm going to talk about relate to two sort of efforts that we have ongoing at the moment. One is the National Wind Erosion Research Network, and the other is the development of the Landscape Data Commons. And we have a large number of people involved in both of these efforts, generally doing multiple things in multiple different areas. And I think that will become apparent through my talk. And this is sort of a bit of a two-parter. So this week, I'm going to give a general overview of what we're doing, and then sort of focus on some of the wind erosion network and sort of related tools and applications and things that we're doing there. And then next week, Sarah's going to talk a bit more about the monitoring side of things, the development of the data commons, and some of the analysis tools that we're developing with NRCS and BLM. So we have a fairly broad set of objectives with these projects. And overall, we're looking at integrating monitoring data sets and models to support rangeland monitoring and management at different scales. So our first sort of objective is to understand more about ecosystem processes and responses to land use, management, and climate using standard monitoring data sets coupled with remote sensing and other kinds of models. We want to be able to assess effects of different management practices and management systems on different ecosystem attributes and services, looking at land health generally, as well as air quality and that kind of thing. And in doing this, we want to be able to leverage the data sets to be able to provide regional context for local experiments and local assessments, and develop our understanding of interactions between land uses and management across scales, from to the field and farm scale right up to the national scale. And a big part of this is developing tools with our stakeholders to inform land use planning and to identify and evaluate conservation practices and restoration options and that kind of thing. And those tools include models as well as data visualization and analysis tools and that kind of thing. So to address these objectives, we have also a pretty broad range of questions. And I've just put up some examples here that go sort of from the national scale at the top down to more of the fine process scale things we're doing on wind erosion at the bottom. So very generally, working with agencies like NRCS and BLM, we're interested in assessing how different land uses and so forth are influencing the condition of ecosystem services across public and private rangelands nationally. We want to be able to develop tools for these stakeholders to assess trade-offs and co-benefits of different land use and management strategies for various ecosystem processes. A big part of this is looking at how we can incorporate monitoring data and new indicators from models into interpretive tools like ecological site descriptions and build analysis tools and workflows that link these pieces together. And then on the wind erosion side of things, we've got some pretty specific questions associated with the network, looking at how much wind erosion is actually occurring across grazing lands, where's it occurring, how's it influenced by different processes, and what can we actually do about it. We also have some pretty basic research projects looking at more of the sort of the fluid dynamic processes and how different soil properties are influencing aeolian transport, which sort of feeds up into building better predictive models that can work with the monitoring data sets to support management. So because we have a lot of questions, we also have a lot of projects, and we have two sort of long-running projects that have really provided a foundation for a lot of this work. And then we have a number of other sort of external collaborations through the LTAR network and through other funded projects that are sort of more on the application side of things. So on the NRCS side of things, we've been working with the Conservation Effects Assessment Project, or SEEP Grazing Lands team, and the National Ecological Site team to develop Aero and applications of Aero, to build workflows for calculating standard indicators from these monitoring data sets, feeding into SEEP grazing land assessments, as well as other modelling efforts, like the water erosion modelling efforts with the rangeland hydrology and erosion model. NRCS have been a big supporter of development of the landscape data commons and applications for SEEP and sort of feeding that towards conservation planning. On the BLM side of things, a lot of our work there has gone into supporting the implementation of large monitoring programs like AIM, as well as developing workflows and tools for analysing the monitoring data and reporting on status, condition and trend of various ecosystem attributes and processes, and really looking at how we can incorporate monitoring data and models at different scales into land health assessments and decision making. And a big part of this has involved development of new applications of monitoring data, like developing ecological site concepts, developing quantitative keys to be able to link monitoring data to ESDs and that kind of thing. Down the bottom, I've just listed some of the other projects that we have going. Of course, the Erosion network is a big part of what we do, and we have a working group within the LTAR network, just sort of that helps us coordinate the wind erosion network. We also coordinate a rangeland soil erosion working group that looks more broadly at erosion processes and ecosystem changes sort of nationally. And then we have some basic research projects looking more on the application side of things about understanding how different ecosystem changes like energy development, invasive species, wildfire influencing wind erosion and dust, and what the feedbacks of that can be. For example, dust on snow impacts on water resources for agriculture and that kind of thing. So this horrendous diagram sort of summarizes all the pieces of the puzzle that we're currently working on. So I'll just sort of talk through this and then look at some examples. So sort of starting in the top left, we have our large standard monitoring data sets like the BLM AIM monitoring program, the NRCS's National Resources Inventory, NRI, the Wind Erosion Network, and various other projects that implement core methods like our DIRT project on the Jornada, projects, other ARS units with USGS, and as well as data collected by sort of the general public. So the idea of the data commons is to harmonize these standard monitoring data sets and then aggregate them in a single database system that we can then link to models, so remote sensing models and erosion prediction tools like Aero and REM. We can then develop various model applications and analyses from those. We're working on a web portal to make the data publicly accessible. And part of the web portal will be a suite of analysis tools that enable users to interact with the data, for example, in an ecological site context, to explore benchmarks and that kind of thing. We have projects that are leveraging the data to develop ecological site concepts, and we're also looking at workflows to incorporate the indicators and model predictions into ecological site descriptions so that they can inform management. And on the left-hand side, we're also working on links with LAMPKS and essentially access to this whole system through mobile apps and that kind of thing. So I'm going to take a bit of a dive into from this sort of big picture into a few things that we're working on specifically on the wind erosion side. So just a bit of an update on where we are with the National Wind Erosion Research Network. I'll then look at where Aero is as a tool for predicting new indicators of wind erosion and dust emission, supported by data from the wind erosion network, and then how we're applying Aero to these large monitoring data sets. And then from there, I'll take a look at just example applications that we're developing, sort of on the analysis side at the broad scale, as well as how we're going about linking erosion indicators to ecological site descriptions with quantitative keys. And then I'll sort of finish up by just taking a quick look at one of the more basic research projects that we have on aeolian processes, which has some really interesting implications sort of in the broader management context. And then, so next week, I think Sarah's going to pick up more on the monitoring side, the infrastructure of the data commons, and these sorts of analysis tools that we're working on. So I guess where we're at with Wind Erosion Network, so we got the network off the ground in 2014 as a pretty large multi-partner effort. We now have, I think, about 18 sites involved in the network in various capacities. The orange markers are sites here that are either partially installed or about to start installations. So we're near complete with the current set of sites we have, although not all of them are actively collecting data. And we've been really successful, I guess, in implementing a core set of standard monitoring methods to measure aeolian processes and their controls across a range of agroecosystems, which just hasn't happened before. So this is sort of the largest standardized aeolian transport network globally now. And we've had some really interesting successes with this, include use of cross-site collaborations on aeolian work, being able to look across different agroecosystems with the same set of measurements and methods, evaluating different processes, and incorporating different people's perspectives, which has been really useful. This has really helped us to raise the profile of wind erosion and dust work in USDA, both within ARS and NRCS, and particularly with BLM as well. And it's enabled us to develop new connections with other agencies like National Park Service, who are now incorporating vegetation height measurements into their monitoring programs specifically so that they can assess wind erosion with Aero. So that's really neat. We've been able to use the data to understand more about aeolian processes and how we go about measuring them in landscapes, and how we might provide and interpret indicators of wind erosion to managers. Interestingly, this has also enabled us to get a new rangeland soil erosion working group going in ELTAR, coordinating with the water erosion prediction folks. And so we're now looking at really new projects to leverage both wind and water erosion models with the monitoring data sets to develop new tools and new interpretations together. So that's really neat. And we've been able to produce some publications from this and are continuing to do so. I guess one of the big things that's come out of it for us at the Jornada and for our partners is the ability to use the data from the Wind Erosion Network to support development of new tools like the Aero Model. So Aero is a physically based sediment transport and dust emission model that lets us use the monitoring data to produce new indicators of wind erosion. And these include the indicators of soil and site stability, as well as dust emission, which lets us say something about air quality and soil and nutrient losses. And Aero predicts a size resolved dust emission, so different sizes of soil particles that have been lifted up in the air, including those less than 10 microns and less than 2.5 microns, which are monitored under the National Ambient Air Quality Standards. So we can start linking what's going on the ground to what's happening up in the air and affecting air quality. So we can implement Aero in a number of different ways, but our focus has been on sort of plot scale applications in a probabilistic mode. So the way that we've parameterized Aero, and this is largely the work of Brandon Edwards, enables us to represent the uncertainty in the model parameters and give essentially sort of probabilistic estimates at the plot level that users can interpret in a risk management sort of context. And we've set up Aero specifically so that it can be applied to these standard monitoring data sets using inputs that can be calculated from LPI, height, and canopy gap intercept methods. So the map on the top right here just shows the extent of the core methods data sets that we have available to run Aero on now. I think about 70,000 locations have been monitored that we can now apply Aero to, which is really neat. And the sort of diagram down the bottom just shows the key processes that Aero is representing. And the outputs are sort of the saltation flux of sediment across the surface and the dust emission up and away from the surface. So when we run Aero, we pull in wind speed data from a regional reanalysis wind speed product. So it's probabilities of wind speed for a location. And then we pull in information about the vegetation height, the distribution of vegetation on the landscape and the ground cover or the unvegetated soil. We can get soil texture information from the monitoring plots or from digital soil maps. And we link that to a lookup table of sort of fairly finely resolved particle size information to be able to represent the dust emission and the soil erodibility. So one of the big motivations for us in developing the landscape data commons was to be able to link models like Aero to the monitoring data sets and run them efficiently. So harmonizing and aggregating the data sets and then developing data models that enable us to calculate standardized inputs to tools like Aero. And so that's what we've been focusing on for the last few years. We can now produce plot level estimates of sediment fluxes and dust emission. And we're now really focusing on how we can analyze and interpret these estimates and deliver them to users in a way that they can actually understand and put to use in a management context. And a focus of this has been interpreting the erosion indicators in the context of ecological site descriptions and state dynamics within different sites. So we have some projects funded by BLM in New Mexico to look at this and the National Ecological Site Team. And one of the things that we've been doing is developing quantitative keys for different ecological sites and states so that we can key the monitoring plots to the site and state level, and then start to look at how different indicators of ground cover and other ecosystem attributes are changing in response to state changes. So you can see from these examples with the gravelly and sandy ecological sites, how the state changes result in different changes in the amount of bare soil, in the spatial arrangement of vegetation and the canopy height. And these all influence the potential wind erosion, which we can quantify with Aero. And we can then look at where there are sort of structural thresholds that relate to this ecosystem sort of state changes that we could set as targets around our management objectives or as benchmarks to help with land health assessments and that kind of thing. So sort of taking this up to the really broad scale, we have a project with the Utah Rangeland Soil Erosion Working Group now looking at how we can apply both Aero and REM to understand more about effects of invasive plants and wildfire on wind erosion right across US grazing lands. So the maps on the left here just show percent cover of some key invasive species or groups of invasive species. And the panel of graphs on the right here shows some potential wind erosion responses to changing cover of invasive species and bare soil across the monitoring plots. So there's quite a bit of information in here, but basically increasing wind erosion, the dots change from green through to red. So this would be increasing erosion here. And we have bare soil cover on the x-axis. So typically the wind erosion risk increases with increasing bare soil. But we find some interesting patterns across different ecoregions and with different invasive species. So in the Chihuahuan Desert here, the main invasive species that we're looking at is mesquite, which has a pretty direct effect on wind erosion. So increasing mesquite cover is typically associated with reduced understory cover and increased sediment transport rates. Whereas in other regions like the Great Basin, where we have cheatgrass and other brome grasses, we see that increasing invasive species cover is typically associated with reduced wind erosion risk as a first order effect. But the second order effect is that those invasive species increase wildfire risk, which can have a massive effect on wind erosion as a sort of a feedback or a second order process. So we're using sort of our site level understanding of the dynamics and the interactions with erosion processes to try to form a big picture sort of understanding of what the interactions between invasive species and erosion processes are. So final sort of example of things that we're working on, I thought I'd sort of drop down to one of our more basic research projects. And since about 2015, 2016, we've been collaborating a lot with the Army Corps of Engineers on projects to understand more about aeolian sediment transport. So the first project that we had that we conducted at the Jornada looked at effects of different soil properties and wind speed on the particle size characteristics of dust emitted from different soils. And that has really supported the selection of the dust emission scheme that we have in Aero to represent that size resolved dust emission. And the last project that we had, and one that we're just starting now, have looked at the effects of vegetation on aeolian transport through what we call the drag partition. I won't go into too heavy detail here, but sort of looking at the image on the bottom left, basically when we have wind blowing over a landscape, it has a shear stress or a force associated with it that becomes partitioned between the roughness elements, the vegetation, which are represented by these cylinders, and the bare soil. So it's the shear stress of the wind on the bare soil that picks up sediment and moves it. So by looking at the ratio of shear stress on the soil surface to the total shear stress, it tells us something about the effectiveness of vegetation at a site in reducing the wind erosivity, essentially. Between February and June last year, we buried an array of pressure transducers in the soil over the Jornada network site. We had 27 of these at random locations. And these pressure transducers were calibrated to measure the wind friction velocity, which is related to the wind shear stress. So this graph essentially shows what the key outcome of these measurements are. So each of these points in the bottom left here are our measurements. And each point represents a daily area average of the effect of the vegetation on the wind. We have a phenocam at the Jornada network site, so we use the green chromatic coordinate from the phenocam data to classify our measurements into periods where the vegetation was dormant, pre-green up, and sort of peak green. And we're able to look at how effective the vegetation was at reducing the wind erosivity as the mesquite greened up and as annuals came up and that kind of thing. So we're able to establish really from a physical basis what the effect of changing vegetation, particularly with the mesquite green up, has on the wind shear stress. And this is, having a big effect on the reduction in sediment transport as we go from spring into summer with the green up of vegetation. So this has been really neat for sort of confirming our parameterization of Aero to represent these kinds of effects. We've also been able to compare our measurements with a similar set of measurements that some folks took at M0 and M-Well back in 2005, 2006. And we can see really quite nicely here what the effect of a vegetation state change from a sort of a shrub-invaded grassland site to a shrub-dominated system has on the potential wind erosivity. So there's effectively a big increase in the potential wind erosivity, which makes sense as we see there are nebka dunes forming at these sites and that kind of thing. And these data also have some sort of nice, not implications, but tell us a lot about what might happen sort of on the restoration or herbicide treatment side of things. So if we were to effectively treat a sort of a shrub-invaded grassland site with mesquite, with herbicide and reduce its foliar cover, we would dramatically increase its the potential wind erosivity at the site unless we got re-establishment of grasses. And if we were to apply such a treatment in a shrub-dominated system, we could have a massive effect on the wind erosivity and really dramatically increase sediment transport. So this is a potential trade-off of a restoration practice that we might want to be aware of. And that sort of emerged nicely from this data set. So I'll just sort of start wrapping things up here. I guess when I started with the Jornada in 2012, we had this vision of being able to develop new indicators and tools to support wind erosion assessments. And the sort of diagram here summarizes where we've come to. So we have the National Wind Erosion Research Network collecting standard observations across different agroecosystems, feeding data into model development like Aero. With the tools that Sarah and her team have been developing, we've now harmonized and aggregated the different monitoring data sets and connected them to Aero, and we can produce new indicators of wind erosion, dust emission that we can start interpreting and providing to the public and managers to use. So sort of what we've got in the pipeline and where we're going with these things on the wind erosion side, we've been waiting literally for months for our Aero paper to make it through peer review. So hopefully first validation of the model will be published soon and we can make the model itself public. We have run Aero on the monitoring data sets in the data commons, and so we have sort of pre-calculated indicators of soil and site stability and air quality that will be publicly available. We're working with NRCS on producing some different erosion risk maps, a soil vulnerability index that's driven by Aero, and an ecological vulnerability index also driven by Aero, but representing sort of vegetation effects on wind erosion. And we're working with Joel and the ecological site team at incorporating erosion indicators from Aero as well as other indicators of ecosystem attributes into ESDs in EDIT. With BLM and NRCS, we're working on an ecological site summary tool to summarize the information and a benchmark exploration tool. And Sarah's going to talk more about those next week. And shortly, we're going to be working on an online version of Aero so that folks can run scenarios, evaluate how changing vegetation cover and wind and that kind of thing might influence potential wind erosion at a site, as well as uploading their own data so that you can visualize where erosion risk at your piece of land might sit relative to local or regional distributions of erosion risk. And part of where we're sort of going with the visualization and analysis tools is heading down the line of looking at how we can use the monitoring data and models to support climate change impacts assessments, as well as more flexible management that's data informed, including sort of more anticipatory adaptation, being able to assess what different trade-offs might be here and now.